So for the last few topics, we've been using the ray approximation to analyse all kinds of image formation and useful things we can do with light. But let's not forget, light is a wave. What are some of the consequences of the wave nature of light? Well, remember, this idea of interference is really important for us understanding that light does behave like a wave. So why don't we see interference all the time? We look around, we see lots of sources of light. We don't seem to see much in the way of interference patterns. Well, it turns out the conditions for interference, particularly for light waves, are actually quite stringent. Really, you need a single wavelength. If you have a whole bunch of different wavelengths, then the crests meeting the crests and the troughs meeting the crests for destructive interference is going to be happening here, sometimes constructively, there, sometimes destructively, varying very quickly in space and in time. In a sense, the interference pattern just washes out, and we just see the average intensity. We really need a single wavelength so that can maintain the phase relationship. Crests and troughs are kind of in the same position. And that second idea is called being coherent. Most of the light sources we see are neither single wavelength nor are they terribly coherent. So how in the world did Thomas Young manage to find interference patterns in the first place? Well, he did a couple of clever things. He really only had sunlight to work with, which isn't an ideal source. But he spent some time doing what he could to make it as single wavelength as possible, using filters. Then he did one other clever thing. Instead of making his light be two sources, he started off making his light just a single source. If we look at a schematic of his experiment, you can see there's a slit here labelled S1 with light coming through the pinhole labelled A. That's a small pinhole where the light comes through and basically acts like a point source of light. All the light, whether it's going up in this direction or down in this direction, has essentially the same phase relationship. It's come from the same point in space. That means when that light illuminates slit 2, S2, and comes through pinholes B and C, the light that arrived there, again, has a nice fixed relationship between the crests and troughs of the wave. Then when the waves spread out from B and also from C and overlap on the screen, we're able to see that dark and light pattern that we know represents the interference of the waves. In fact, if we were to look at a photograph of such a screen, we would see a whole bunch of bright and dark bands. And from their spacing, we could tell all kinds of things, such as the wavelength of the light that was being used. If instead of just a single slit, we had a whole range of slits, we could do even better. If we had, say, a whole row of very, very closely spaced slits, we'd be getting interference from each pair of those slits, and the interference pattern becomes even more well-defined. In fact, in modern-day interference experiments, this idea of an interference grating is used all the time. We can see something quite similar if we look at the light reflected from the surface of a CD or a DVD. What we'll see in that case is a kind of rainbow pattern of reflection. You're seeing interference of different colours occurring at different points in space and time. All the little bumps and grooves on the CD or DVD are acting like small sources of light, many of them very closely spaced at just the right range to give us interference of optical light. Now, the next thing we're going to look at as a phenomenon with wave interference has to do with the idea of trying to get rid of reflections in unwanted situations. For example, in a camera, you might want the light to move through the lens. You don't want a whole bunch of extra reflections putting light where you don't need it. How can we possibly get rid of a reflection off some interface? Remember when we did Snell's law and refraction, we know that whenever light passes from one medium to another, there's a transmitted part, the refracted wave, and a reflected part. Well, as you see in this diagram here, the wave comes from N1 into N2, and there will be some reflection at that interface. That might be the light we want to get rid of. One way to get rid of it is to make some extra light that is going to interfere destructively. So we can, in fact, put a layer of some additional material on there with a cleverly chosen refractive index and just the right thickness here so that the wave that reflects off the top of it interferes destructively with the original wave that we had, and that cancels out these two waves. This is sometimes called an anti-reflection coating. Now, it's actually very critical that we have just the right thickness of material. In fact, it has to be done just so on the scale of an optical wavelength. That's a very hard thing to do. No one has a ruler that can measure that very easily. But instead what you do is during the coating process, when you're making these thin layers, these anti-reflection coatings, you actually have light going through the material and you monitor the reflection. and then as the reflection reaches its minimum, you know you've got just the right thickness so that the two reflected rays are interfering destructively. And this is just one example where the idea of optical interferometry gives us really quite precise and exquisitely fine detail in our measurements. Now, in the next topic of the module, we're going to actually depart from much of what we've been talking about with light as a wave. We're going to meet some entirely new phenomenon that will make us question everything we've done and prove to us that indeed the universe is a very strange place worthy of our investigation.